I got some feedback that math is tough, which isn't surprising. So I thought I'm going to go a different direction. I'm going to look at quarks like a kid. And my inspiration for this is Nobel laureate David Gross. He wrote this article at the middle school level about quarks, and it's not bad. And it even includes some ideas about string theory that may indicate a unifying effect between electrons, neutrinos, and quarks. So let's get started. And in order to start, what I'm going to do is talk about some pictures from this article and talk through them to see if I understand what's going on. And what's nice is this article goes from Rutherford through current day thought processes, including Murray Gell-Mann and his idea of quarks, who came up with that, what I consider not the best name for a particle, but he came up with the idea, it was accepted, so we have to live with it. First picture. This is back with Henri Becquerel, trying to say his French name correctly. And this is one of the first discoveries about any kind of thing that was radiation, which ended up being elementary particles. And what he noticed was he put this radioactive element in an area so it kind of forms a beam. All the particles go out this way. And then he had a magnetic field that deflected the particles, what he considered particles, and into three different types of things, or three different areas of this photographic plate. So if you notice, one of the particles, or you can call it particle-like, goes straight, it's not deflected, so that would mean that it has no electrical charge. This happens to be gamma rays. And one of them is deflected to the left here in the picture, which means that it's either positive or negatively charged. And this other one is the opposite charge to it. So what happens is that we come up with three different kinds of what we eventually ended up calling particles. One of them is an alpha, one of them is a beta, and one of them is a gamma. Now, why choose those names? Well, the first three letters in the Greek alphabet, alpha, beta, gamma. So I'm choosing this as alpha because it's not deflected as much. It has higher mass. The electron is deflected more, so it has less mass, so it gets deflected more. Another picture. Notice alpha. That's one of the three types of particles that Becquerel tried to say French things, but anyway, this has its alpha particle, which is a big deal because the alpha particle is more massive. It was deflected less, and Rutherford had this set up. Notice we try to make a beam. We've got a alpha particle emitter, which is radium or uranium, which emits these things. We could talk about how uranium is radioactive and it causes this, but for right now, we have this sample here that produces the same kinds of things that Henri came up with, and we send this thing through this slit, and all around it is a special coating of glass that causes the deflected items to show up on the screen. So most of the time, these things just go straight through, even though and this is gold foil as it shows, but most of them go straight through, and every now and then one bangs off the interior. So this gives the view of the atom and that there's a nucleus. So let's talk about what I just said. Well, I said that there are alpha, beta, and gamma particles. Oh, by the way, gamma happens to be photons, really high energy photons, and we call them gamma. But this is uh, the picture that we get. So all that comes out of this is not the elementary particle proton yet, but it's this nucleus thing. So different types of atoms. This happens to be gold in this case. Has a lot of protons and neutrons in it. And anyway, we've got this thing of a nucleus and a whole bunch of empty space. Now, how do we get to the idea of a proton, which was uh, Rutherford's name, and proton is some kind of Greek word for first. But anyway, the proton was discovered as a charged particle if you ionize hydrogen. Remember, we talked about hydrogen as the simplest atom. If you ionize hydrogen, then you get just a proton left over, and you can start studying the properties of the proton. So we have had the electron, elementary particle. We've had the electron neutrino that we talked about in carbon 14 decay, which was just not a discovered particle at that time, but we just made up a particle so that the math could come out right. So otherwise the mass defect wouldn't make much sense. Then we've got a proton. And then we have some uncharged particles, which are called neutron, which means just neutral charge. So proton came first idea, then the neutrons, and it turns out that neutrons have a little bit higher mass than the proton. So where do we go from here? Is the protons it? Well, what was the title of this whole series? Was In Search of a Quark. So let's quickly go to the current understanding of quarks. Let's get into quarks, and then we'll understand why maybe we need to talk about some more specific math that came up with this. So the math gets really complicated. So anyway, here's quarks. Here's how we understand them. The up and down quarks, notice up and down, quarks in a proton and a neutron, that's most of our mass. So let's focus on the up and the down quark. And then we'll talk about the flavor, which could be a charm, a strange, a top, and a bottom. I don't know about these, but these aren't part of mass, so let's hold off on those. If we can understand or get some idea about up and down quarks, then we're talking about most of the mass that we live with. The charge, rather than an elemental charge, it has fractional charge, either a minus 1/3 or a plus 2/3. And then it also has a color, red, white, and blue. How patriotic is that? Here's the proton, an up, up, down, and a neutron is up, down, down. Now, if I calculate these charges correctly, I should come up with a positive 1 charge for the proton and a neutral charge or 0 charge for the neutron. Let's see if that works. Okay, 2/3 plus 2/3 gives me 4/3. I subtract, which is 1 1/3, and I subtract 1/3, that gives me a positive 1 charge. Let's go down to the neutron. Up quark is 2/3 charge, Down quark is minus 1/3 and minus 1/3, plus 2/3 minus 2/3 gives us a zero charge. Now, review, what are the four fundamental particles that make up most of everything that we experience, and not Big Bang type stuff or super accelerator stuff? Up quark, down quark, electron, easiest to understand, and a electron neutrino. Now there's more than one kind of neutrino, that's why we say an electron neutrino. Finally, we get to string theory, which, if you notice, I've got 1, 2, 3, 4 different pictures of, they look like little spirograph pictures where we have different types of formations of frequencies or strings or whatever it is. Now, the string theory gets really messy, and I've got a couple books about string theory. Haven't even been able to crack the cover yet because I'm not ready mathematically. But anyway, here's the electron string setup. Here's the quark string setup, the neutrino setup, and what we haven't talked about is we can't forget about the photon itself. So string theory says that all of these individual named things can all be represented by a theory where everything's made of a thing called a string. So strings tie all these different things together. So we've jumped all the way up to current thought processes. And the Nobel laureate is today, he's 80 some years old, and he's working on string theory and how to unify all these kinds of things.